Hello again, Dr. Maxwell here, and in this lecture we are going to cover section 4.5 and talk about concavity. What do we mean by concavity? Well, we have two terms down here, concave up and concave down. Concave up, which sometimes I abbreviate CCU, is when a function's graph is shaped like this. You can think of this as it would hold water. Now concave down, on the other hand, which sometimes I abbreviate CCD, is when the graph has this orientation. This does not hold water. And look what it says here in our definition. It says a graph is concave up if the first derivative is increasing. Okay, well, if you look here at the graph of y equals x cubed, at 0, my derivative would be equal to 0 because there's a horizontal tangent. And then gradually the slope of the tangent line increases, which means the derivative increases. When you're concave down, on the other hand, your first derivative is decreasing. You can see that down here it's pretty steep, and then it gets less steep, less steep, less steep in terms of the slope of the tangent line. Now, here is the cool thing. We have a test for concavity that involves the second derivative. If the second derivative is negative, then our function will be concave down. I did this in the wrong order. And if our second derivative is positive, our original function will be concave up. So let's examine this graph in a little more detail. F of x equals x cubed. The first derivative is simply, let's see, f prime of x equals 3x squared. And the second derivative, f double prime of x equals 6x. Okay, so the first derivative has a critical point at x equals 0. And the second derivative is 0 when x equals 0. So we are going to determine when the original function is increasing and decreasing, and look what happens at 0. And we'll do that by looking at the first derivative. So let's test the first derivative. Over here, I might pick negative 1. If you plug negative 1 into the first derivative, that's positive. In fact, can you tell that the first derivative is always positive? Except at x equals 0, because it's equal to 3x squared. So we're also positive over here. What does that say about my original function? That I'm increasing everywhere. So I know f is increasing from negative infinity to infinity. Alright, so what does the second derivative tell me? This will tell me about concavity. We do the same sort of thing. You might think of 0 as being a critical point of the second derivative. Sometimes a book will call this a second order critical point. But I just focus on finding the zeros of the second derivative. And what we want to do, if you go back here, we want to see if the second derivative changes signs, because when it's positive, we're concave up. And when it's negative, we're concave down. So that's why we test at the zeros. So I will test again, -1 and +1. We plug -1 into the derivative. Of course, that's negative. If you plug +1 into the derivative, that's positive. So what does that tell me about my original function? Over here, because the second derivative is negative, the original function is concave down. So this would be concave down from -infinity to 0. And over here, it's concave up. And this happens from 0 to infinity. Okay, so the first derivative tells us about extreme values and whether the function is increasing or decreasing. The second derivative tells us about concavity. So these are things that we're always going to be doing now when we want to examine the behavior of a function. So let's write up what we know. Here is the graph of my original function. And you can see, hopefully, if you look at the piece where x is below 0, if you continued this on, you can see that it's concave down. And likewise, if you look at the piece that is greater than 0 over here, when x is greater than 0, if you sort of continued that graph, you can convince yourself that it's concave up over there. All right, so what do we want to say? The graph is increasing from -infinity to infinity. Remember, it was always increasing. The graph is concave down from -infinity to 0. The graph is concave up from 0 to infinity. And there is an inflection point, which we haven't really defined yet, at the origin, at 0, 0. This is a change in concavity. We call the place, where we switch from being concave down to concave up an inflection point. And here is the definition of what it means to be an inflection point. And this is key here. How do we find inflection points? Well, this might sound familiar, but we want to find places where the second derivative equals 0 or the second derivative does not exist. So these are like critical points for the second derivative. We can use the second derivative in another way. there's a second derivative test for local extrema. Okay, so let me go through this. Why do we have this? Well, sometimes it is more convenient to use this test. For us, we probably won't use it that often, if ever, but it is important to understand why this works. So let's look at number one. Number one says my derivative equals 0, and my second derivative is negative. Remember, a second derivative being negative means my original function is concave down. First derivative being 0 means I have a horizontal tangent, so that looks like a max. Concave down and a horizontal tangent. That is going to give us a maximum. Number 2 here says, this is number 1, my pitiful picture for number 1. Number 2 says, again, the first derivative is 0. The second derivative now is positive. When your second derivative is positive, your original function is concave up. When the first derivative is 0, we have a horizontal tangent. So that is a minimum. And then, so this is number 2. For number 3, we have the situation where the first derivative equals 0 and the second derivative equals 0. And here, well, unfortunately, the test fails. You would have to do a little more work to figure out what's going on. In other words, you would have to test either side of the first derivative. What's an example of when this happens? Well, we just looked at one. Y equals x cubed. If you go back and look at this graph, there was no extreme point there. The first derivative was 0 and the second derivative is 0. Okay, so let's do first. This is Dr. Maxwell's silly trick for remembering how does the test for concavity work. If the second derivative is negative, this is how I remember it. If you're negative, you have a bad attitude. And you're probably sad. So you're not smiling. You're concave down. I know it's silly, but it helped me. On the other hand, the second derivative is positive. Well, you have a good attitude. And you're happy. Because you've got a positive attitude. And when you're happy, what do? You smile. And you're concave up. Maybe that helps. Maybe it doesn't. Use it if it does. All right, here comes the hard work that we need to do. Curve sketching. So we are going to try to sketch the graphs of these 3 functions. And this is just a procedure that we go through. And the order doesn't really matter here, but we want to check the domain, ask ourselves, is there any symmetry? Find the derivative. Find the second derivative. We want to identify local max and mins, identify increasing and decreasing intervals. Then we're going to look at concavity. We need to be aware of asymptotes. And then we put all this together. We plot intercepts, extreme values, and inflection points, and try to sketch the graph. So here is our first function. This is a nice polynomial. It's 4th degree. it's going to have an absolute minimum because it has a positive leading coefficient. I already know that I'm looking for that. There might be some local extreme values. We'll have to test for that. So the domain is all real numbers. Let's find the first derivative. Bring down the 4. So I have 4x cubed minus 12x squared. Now I'm going to be wanting to find the zeros, so I'm going to go ahead and factor this by factoring out 4x squared. That leaves me with x minus 3. A second derivative will be 12x squared, I'm looking right here, minus 24x. I also want to know when the second derivative is equal to 0, so I'm going to go ahead and factor this. Pull out 12x, that leaves me with x minus 2. Okay, critical points come from the first derivative. We have critical points when the first derivative equals 0, so that happens at x equals 0 and x equals 3. What do we do next? We set up our test intervals, which I've already drawn down here. So here's 0, here's 3. Now, my derivative, we're going to be checking the sign of the first derivative. In this factored form, I'm going to test negative 1. If you put negative 1 in the first factor, that's positive, because 4x squared is always positive or 0. If I put negative 1 in the second factor, that will be negative. So my derivative is negative in this first interval, which means my original function is decreasing. Okay. I think I'll test x equals 1 in this second interval. Of course, you plug 1 into 4x squared, that's going to be positive. You plug 1 into the second factor, that's going to be negative. So, interesting. I did not change from increasing to decreasing there. And over here, I will plug in x equals 4. Of course, the first factor is still positive, and now the second factor is positive. So my original function is increasing. So we have an absolute minimum at 3 and whatever f of 3 is, which we will have to calculate. So I did that calculation for us. It turns out to be negative 17. We also know that our function is decreasing from negative infinity to 3. That's where the arrows are going down. First derivative is negative, and increasing on 3 to infinity. So in case I said that wrong, decreasing from negative infinity to 3, increasing from 3 to infinity. So let's now go to the second derivative. We want to figure out concavity and identify any inflection points. So the second derivative equals 0 when x equals 0 and when x equals 2. So just like we did for the first derivative, we're going to set up test intervals for the second derivative and determine concavity. So we're going to test the sign of the second derivative. Again, over here I can test -1. If I put that in the first factor, that would be 12x, so that's negative. If I put that in the second factor, that is also negative. Two negatives give me a positive. So my second derivative is positive. Do you remember what that means about the concavity? If you're positive, you have a good attitude, and you are smiling. So we are concave up. Okay? I gotta stop saying okay. Let's test x equals 1 in the second interval. My first factor is positive. My second factor is negative. So overall, my second derivative is negative, which means I am concave down on this interval. Lastly, we can test x equals 3. That will be positive and positive, so my second derivative is positive, and now I am concave up again. So we have two inflection points. I like to abbreviate them IP. This will be at 0 and f of 0, and at 2, f of 2. Why are these inflection points? Because we change concavity. So this is pretty easy to figure out. This is 0, 10. F of 2 is, well, let's just do it up here. 2 to the 4th power is 16 minus 4 times 8, which is 32, plus 10. And this will give me negative 16 plus 10, which is negative 6. All right. Let's also write down the intervals where we're concave up and concave down. So this will be from negative infinity to 0 and 2 to infinity. And we're concave down on 0 to 2. Now we are going to try to sketch the graph. I have summarized the information that we have gathered using the first and second derivatives. We have a local and absolute max, and that's not right. We have a local and absolute min at 3, negative 17. Let's put that about here. This is kind of hard on the iPad. Okay, an inflection point at 0, 10. Add 1 at 2, negative 6. So that's where we change concavity. So let's see. I am concave up, so this takes some practice, but I'm concave up from negative infinity to 0. So I'm going to try to draw that as concave up. Then at x equals 0, I change and from concave up, and I'm concave down all the way until I get to this next inflection point. Now I am concave up from this point on. So this is just how you go about trying to sketch the graph, and it does take some practice. But here is my absolute min. Here's an inflection point. And here is another inflection point. And I know that the end behavior of the graph is correct too. This is a fourth degree polynomial. Now if we let Desmos graph the function for us, it does a much better job. And here you can see more clearly, I think, that this really is a change in concavity. I'm concave up, then I change, I'm concave down. This is kind of subtle, this change here, but I do change to being concave up, and then I'm concave up from then on. We have a local and absolute minimum. We have two inflection points. Okay, so we will do some more examples in part 2. I have a cool new color, purple. All right, remember to pause the video anytime you want to and write things down, write down your questions, and then send me your questions. Either preferably use the discussion. Otherwise, send me an email, and maybe I can help you out.